Welcome to my talk. My name is Balint Veto from the Technical University of Budapest, and I will talk about the tilings of the Aztec diamond on a modified domain. This is a joint work with Patrick Ferrari from Bonn, and you might be familiar with the Aztec diamond domain that is on the left-hand side of my slide. And the task is to tile this domain with dominoes of size 2 that are either horizontal, so these are the 1 by 2 dominoes, and they're either vertical, which are the 2 by 1 dominoes. What we do is that we take all possible tilings of this domain of size 4 in this example, and then choose one at random from all of them, and this will be our random tiling. And this model was introduced already in the early 90s and well studied also since then. Here is an example for a tiling of this particular small Aztec diamond, and what we will be interested in is the following. You can see that on the right-hand side of the picture, these 3 dominoes are all vertical. And these 3 vertical dominoes can only be located in a very, very regular way. So follow this brick-like pattern. And actually, these 2 vertical ones, this and this, are also in a region that that starts at this corner and follows this this symmetric pattern. And as you increase the size of the domain, you will see that actually not only a few of these dominoes, but also macroscopic portion of them will follow this regular pattern, and this we call the so-called polar region, because they are close to the 4 corners. And by symmetry, of course, it is enough to consider one of the corners. We take the top one, which is called the north north corner, and therefore we call this region the north polar region, that consists in this example only from these 2 dominoes. It has a boundary that is a random curve, and we are interested in the fluctuations of that random curve. More precisely, to each tiling we can map, we can associate a line that will cut several dominoes, but dominoes that are above this line are members of this north polar region. And it was proved already more than 20 years ago that as the size of the Aztec diamond tends to infinity, then this boundary will converge in some sense to a circle. Here is an example. Here is a simulation picture that has a larger size, and here you already can see this circle-like boundary, which is still fluctuating. So later, in 2005, Johansson proved that if you take xn to be the boundary of the north polar region in a domain, in a tiling of a domain where the domain has size n, then after appropriate scaling, this boundary converges to the Airy2 process minus a parabola, where this RE2 process is a typical process, typical limiting process in the KPZ Carter-Parisi-Zhang universality class. And the rescaling of this curve is the following: that it has a certain linear first order size that is, in order to be really around this circle, we rescale time. I mean, we take horizontally a piece that has size n to the 2/3, and the fluctuations of this curve is n to the 1/3 that we divide by, and in this way we get a limiting process. The sense of convergence is in a pretty strong sense because it is a process convergence in distribution. What we are interested in is the following: the model, how we modify the Aztec diamond, is that we cut off a piece from the Aztec diamond around close to the top corner. And we cut off it with a horizontal line, and its height is at constant C1 times n, where this C1 is the same C1 as in Johansson's paper. This is the most interesting leading order, because if we took something larger than C1, then it has no effect in the limit on the behavior. If it is smaller, then also we expect something slightly interesting happening. Actually, this Arctic circle is modified, and we have a guess what is happening at the point of tangency of the restriction line and this Arctic curve. But still, in some sense, the critical case is when we take C1 times n, then the Arctic circle is tangential to this at first order, and we add some parameter r, which can be arbitrary, a real number, times n to the 1/3, which is the fluctuation order of the Arctic curve. And now what we do is that we take the remaining domain and pick a tiling that is uniform from all possible tilings of that restricted domain. We can say equivalently that that we keep the part that is above this line to be all horizontal, and we call x and r to be the boundary of the North Polar region in this case, in this restricted model. There is still some polar region, which might be also empty. And our theorem is that if we rescale it in the same way as Johansson did, then there is a convergence to a certain non-trivial process, that is the RE2 process minus parabola, conditioned to stay below a constant level r for all times. And we have a convergence in terms of the continuum statistics, which means that probabilities of staying below certain given curves, and also in terms of finite dimensional distributions. And this RE2 process minus parabola condition to stay below a line arises from a more general process, or not a more general process, from a process that is the hard-edge tacnode process that has infinitely many lines, actually. And this one that we get a limit here in the previous slide is just the top line of this hard-edge tacnode process that we described a few years ago in the model of non-intersecting Brownian bridges that are conditioned to stay below a constant threshold at all time. And also the correlation kernel of this hardest tacnode process is given in this paper, what I'm now referring to. And in this case, when we talk about the Aztec diamond, this is the top line that we actually get. And some ideas of the proof is that I already showed you that that there is a way to associate one line in the Aztec diamond, in a tiling of the Aztec diamond, following these rules. But if you follow these rules, you don't only have one line, but also a line ensemble which is non-intersecting, and it corresponds to the tiling. And the way we started our proof was that we gave a random walk representation for a version of this line ensemble. And this was the main idea. And here I want to stop now and thank you for your attention.